Purpose for today and for tomorrow is to review. You've got, of course, your exam coming up on Thursday. A number of you also have other obligations, White House concert on Wednesday and such. And so it's just a challenging time for you. I've put out, I don't know if I put out all three, but I have a total of 3 review assignments for you. The true-false questions that you found, midterm review number 1 that you also found, and review number 2 I'll put up tonight. None of those 3 are for a grade. So you may choose to do them, or you may choose to do as much as you need to, or as little as you need to. I'll know who's ready. So there it is, yeah.
Could those questions on the exam be like that, sort of similar to that?
A format of question that I have used before, it's not common, but I do use it. I usually put one is, which
Like they'll mostly be about definitions of
are true. And then I'll give you a statement 1, statement 2, statement 3,
Oh, okay.
and then you have 1 only, 2 only, 1 and 2, none of these. Yeah.
I know, like for some other AP midterm, AP Tech, like not yours, but official ones, like they took out the all the above or none of the above. Did they take it out for Calc too, or?
I haven't heard any such, but I will check again. There's a big change coming next year.
What would change here?
Some topics are being added, taken away,
Okay.
and so on and so forth. So I will check all those details early next year.
So seriously, how many scratches will
Yeah, we'll figure out how, I'll figure out the schedule and how it works. Are you sure Thursday is the Sunday schedule?
Yeah. I talked to Mr. Larson.
Okay, I'll double check that, and we'll make sure that the schedule works out. Okay. So in light of that, then, you had some true-false questions last night. Does anybody have any questions about any of those?
I have a question for question 6 and question 8.
Okay. Let's pull those up and see how they go.
Think. There are the answers. Well, that doesn't help. Okay, calculus AB. Okay. Answers. Midterm review. True-false questions. There you go. Pull that up. Also, at this time, we're going to check and see how many of you have actually made a contribution to the study guide as you were required to do.
I put my name on it because I did mine, but then there were other additions, but none of them had names on them.
What? What do you mean none of them had names on them?
At least that's what I thought.
No, that is true.
But
I didn't
you
put my name on
notice,
it.
yeah, I didn't
put
see
my
any
name on
names,
it.
so I didn't do that.
What were the directions, Heidi?
Well, I know what the directions were, but
Okay.
I was confused because I thought something changed, or I don't know.
Yeah.
There's no names on it.
Yep. So seriously, follow the directions here, because right now only a few of you, Justin, Tife, Josh, Joseph, Luke, and Will. And that's it for people that get credit.
I did it too. I put my name on the
Where is it?
low zero. It's done.
Yeah, it says under roles.
Oh, you did that one? Joseph, I thought you said you did that one.
Which one?
Raleigh's theorem.
I did do Raleigh's theorem.
I wrote my name now.
I did Raleigh's theorem.
Okay.
Oh.
Yes. Okay, well, yeah.
I don't know how to put the name
Wait, are
on
we
it.
supposed to write our name for every one that we've done?
No, just for the one you did last night.
Okay.
Okay. That's better. I will give you till 3 o'clock to do something useful for the community. Yes, ma'am.
Well, I did it, but it doesn't show up in there.
The way to make it show up is really simple. You just highlight some text right here. Highlight some text right there. Right click and comment. And you can type a comment right there. Yep. Yep. How many of you get these pictures showing up? And how many of you get other weird stuff showing up?
I click preview.
I have to
Yeah.
click preview to make it happen. Yeah.
I
The,
don't think it's the Google Docs app. If you open it in it,
Is that a question mark?
no, or if you like go in.
Google Docs. If you do it and you click on it, it should say open as preview.
I'll try to replace the graphics with the actual equation stuff. So that we can all do what we need to do. Okay, so here are true false questions, and you had questions about number 6 and 8.
Yeah.
If f is continuous on 0 to pi, and f of 0 equals 0 and f of pi equals 2, then there is no c such that f of c is equal to 3.
I'm definitely know for a fact that it's false, because I know that there are instances where, say, that C equals 3 could be a critical point in common
Yeah,
fact.
right.
I just couldn't give any examples that could counter it. I wasn't
Yes,
sure.
so a counterexample could be an equation. Coming up with an equation for this was kind of challenging for me. It took me a couple minutes to work out one. But just a graph would do. If I draw a function so that f of 0 is 0 and f of pi is equal to 2, and lo and behold, my function hits 3 right there, then that's a good counterexample.
Okay.
That's a perfectly valid counterexample.
So, in response to that, I just put it as not true because it's not inherently false, but it's also not true either.
Okay, so actually that's not quite correct. In mathematics, a true statement is any statement that is always true. And a false statement is any statement that is not true. So if a statement has even one exception, such as primes are odd, there's only one exception to that statement. 2. That's a false statement. So any statement that is not fully 100% totally true is false. Maybe is not a mathematical thing. Okay. Suppose f is continuous on 2 to 5, and f of 2 equals f of 5 equals 8. If f has no horizontal tangents on 2 to 5, then f must have a point of non-differentiability on 2 to 5. Okay, what's your question?
Well, see, I wasn't really sure what to answer, because I kind of thought that even though there's a point of non-differentiability, I didn't think that was really possible, because I mean, I know that they say the 2 points are like this, but I could have thought something could have come around and still connected to it. But then I see your answer says that it's true, and that it isn't right, then, so I kind of just got confused, but then how to like picture it and how to know.
Yes. What you were doing, and it's not a bad thing, is that you were trying to picture what was going on and then use that picture as a model to answer the question. And the limitation of that is that I might not be able to imagine sort of the right picture that is an exception. So Josh, back to your thing, what we're trying to do with statements that are false is we're trying to find like counterexamples. We're trying to find exceptions. If I can find an exception, the statement's false. So the problem is that when you create a model and you think it's probably true based on the model, that's tough. So instead, what we're going to do is we're going to check the official legal language. And from this, we're talking about continuous, and we're talking about tangent lines, and we're talking about f of 2 and f of 5. That screams mean value theorem to me. Does everybody see what I'm saying? You understand what I mean? Okay. So I bust out the conditions. I write down, on my paper, I will write down, if f is continuous on 2 to 5 and differentiable
on 2 to 5, then there is a C in 2 to 5 such that f prime C equals f of 5 minus f of 2 over 5 minus 2. And now I know both of those values are 8, so that f prime of C is equal to 0. Aha! Easter egg. That was the little key that unlocks this thing, because I have found that if f is continuous and differentiable, then f has to have a horizontal tangent. And it doesn't, because it does not. Therefore, it fails one of those two conditions, and I already know it doesn't fail this one. So this must be the condition that fails, so there must be a point of non-differentiability. This was definitely the hardest out of the 8 questions. Did that logic make sense to everybody? I want some of this or some of this. Good? Yes? Okay, good. Excellent. Any other questions about the true false? All right, let's talk limits. We had some definitions and we had some theorems. And the limit as x goes to c of f of x equals L means, say it with me if you can, f of x is arbitrarily close to L when x is close to but not equal to c. Very good.
Still middle school.
So, what is the common student thing is to forget where the arbitrarily goes, or to get the C and the L mixed up, so on and so forth. You want to have this definition down word for word. Now, how do we actually find limits? We actually have a number of different ways that we can find limits, and those ways are all on the table. So you want to have all of those ways under your fingertips so that if one way doesn't work, maybe you can try another. How do we find limits on the calculator? How do I find the limit using a calculator? Yeah.
You check a value on the right that's very close to but not equal to the one you're checking.
Exactly. What button am I looking at? Trace. Exactly. Trace will put me to a place on the curve. If I need a limit as x goes to 2, then I would trace to a point such as x equals 1.9999 or 2.0001. The 1 on 2.001 would be the limit from the right, and then 1.999 would be the limit from the left. And those two have to be equal in order for the limit to exist. Yes, very good, very good. Okay. But I will not, if I'm trying to find the limit as x goes to 2, check what value? 2. I will not check x equals 2. It is irrelevant to my limit. Okay. So graphing calculator. Limit properties. Sum rule, product rule, constant multiple rule, difference rule, quotient rule, power rule, or limits. All of those limit properties are useful to us. And that led us to a couple of theorems that were helpful. The polynomial theorem. If P is a polynomial, then I can evaluate the limit with direct substitution. And that saved us a lot of work. We liked that. Likewise, if
if R is a rational function theorem, then I can evaluate, what is a rational function again?
That's quotient of two polynomials.
Quotient of two polynomials, that's right. But there's a catch. There had to be a catch because of quotients. What is the catch? It cannot, what cannot be zero? Q cannot be zero. Very good. That's the catch. What happens if Q of C does equal 0? Then that led us to a second theorem, the alias theorem. What does the alias theorem say? Two functions are equal to each other except at x equals c, their limits are the same. And so we used that to come up with a method for dealing with Q of C equals 0. We use that for the cancellation method, where I have two functions that are the same except when a common factor cancels. So we state in the alias theorem, if f equals g, except at c, and the limit of f equals the limit of g. And that led to cancellation technique and rationalization technique. What is the flag that identifies when I can cancel? What do I look for? The form. And our slogan was, when evaluating a limit, you check the form. That's exactly right. And specifically, what form am I looking for that would tell me that I have a common factor that I may cancel? 0 over 0, which is called the indeterminate form. Very good, very good. What other forms did we encounter?
1 over 0 to be indefinite.
1 over 0, right. Which is not, we just call it k over 0. It's called the, not indefinite, the infinite form, because it indicates that my limit is infinite. That's right. So my graph will have a, what kind of? Vertical. Vertical axis. Good cancellation, rationalization. And that was the alias. Now, if the alias theorem failed us, then we had one other possible tool for use, and that was the squeeze theorem. The squeeze theorem was kind of specialized. Yes, sandwich theorem, that's right. Thank you. Your book calls it sandwich, old school is squeeze, same thing. And the squeeze theorem says that if f is squeezed or sandwiched between two functions, and those two functions go to the same limit at c, then f also must go to that limit. And the picture that we draw is that here is my f, and here is my h, and here is my g, and because f is trapped between h and g, if they both go to L, f has to go to L as well. And we use the squeeze theorem in a very famous limit situation. one of our three famous limits. Let's actually get all three of them here on the board. The limit is theta goes to 0 of sine theta over theta. And second, like unto it, the limit is theta goes to 0 of 1 minus cosine theta over theta. And the third, the limit as h goes to 0 of e to the h minus 1 all over h. What are the values of these limits? This one is 1. This one is 0. This one is 1. There you go. This one we proved with the squeeze theorem. This one we proved by rationalizing, multiplying top and bottom by 1 plus cosine theta, and using this limit right here. Do you want me to go over that? Yes? Okay, not a problem. I have this limit. First thing I do is I check the form. 1 minus 1 over 0. So my form is 0 over 0. I can do something here. I'm going to rationalize by multiplying top and bottom by 1 plus cosine theta. Now you remember, yep. And what do I get as a top here? 1 minus cosine times 1 plus cosine would be
1
minus.
cosine squared.
which is the same as it's the same as 1 minus cosine squared theta. Sine squared theta, right? That's our trigonometric identity, Pythagorean identity. And now the second trick to this is to peel off a factor of sine theta over theta, leaving behind all the other factors. This is our famous limit 1, and this goes to 0 divided by 2, which is 0. And the result is 0. So there's some rationalization. Let's see here. Speaking of infinite forms, if my limit turns out to have an infinite form, then how do I find whether it is plus infinity or minus infinity? Keep betting. Sign analysis, that's right. So sign analysis for infinite forms. For example, the limit as x goes to 2 of 1 plus x over 2 minus x. I check the form. When I check my form, what is that form? 3 divided by 0. That means my limit will be infinite. My graph will have a vertical asymptote. That's right. And so the question is, will the graph go to plus infinity or minus infinity? I actually have to check left and right separately because they can do opposite things. So my first order of business is to split this up into the limit from the left and the limit from the right. And when I check from the left, I am going to be looking at 1 plus a number very close to 2 is going to be positive. It's going to be close to 3. But in the bottom, 2 minus a number less than 2 will be positive. And so therefore, this limit is positive infinity. On the bottom, 1 plus a number close to 2 is still positive. 2 minus a number bigger than 2 will be negative, and my limit goes to minus infinity, just like that. Please notice that your sign analysis belongs over here. The only thing that should be equal to something is the limit is equal to plus infinity or the limit is equal to minus infinity. Do not tell me that the limit is equal to plus over plus. That makes no sense. Okay? The sign analysis is scrap work. It belongs in the margin. Question?
Will we be required to graph a rational function on their exam?
Yeah, that's a very good kind of question for me to ask. And
The graphing of rational functions takes place by figuring out your framework, zeros, points of discontinuity, vertical asymptotes, and horizontal asymptotes. And that brings me to horizontal asymptotes. Y equals L is a horizontal asymptote of the graph of F if what? That's it. There's one other possibility though. And the limit as x goes to negative infinity equals L. Good study. Good job. And so here's an example of a function with a horizontal asymptote. True or false? A function can cross a horizontal asymptote. True. So this is a good example of a function with a horizontal asymptote L as x goes to positive infinity. And it has a different horizontal asymptote M as x goes to negative infinity. And we can read straight off the graph. The limit as x goes to positive infinity of f is L. The limit as x goes to negative infinity of f is M. Does that make sense to everybody? If I am confronted with a limit at infinity, for example, the limit as x goes to infinity of 2 plus x squared over x times 3x minus 1, then what is the tool of choice for evaluating limits at infinity? No. There's no factorization possible. Yeah.
N modeling.
I want N models. That's exactly right. And the reason I want the N models is that the terms that are of power lower than the highest power really don't matter for large enough x's. So that I can say that this limit is equal to, the limit as x goes to infinity, what's the N model for the top right here? X squared. And what is the N model for the bottom right here?
3x squared.
3x squared. It'd be x times 3x. Giving me 1/3 right there. And if you're not sure early, you can multiply it all out. But I just do N models for each factor, right? X times 3x.
I forgot.
Yep. And there it is. And that tells me, since my limit at infinity was 1/3, that tells me that my function has a horizontal asymptote. And what is that horizontal asymptote? It is the line y equals 1/3. Is my horizontal asymptote 1/3? No, 1/3 is a number. The line y equals 1/3 is a horizontal line. Yeah.
I have a question.
Yes.
I remember when we did N models that sometimes there would be like, it'd come out to be like 1 over x after. What did that?
That could totally happen. So let's say I have something like this, right? And that gives me the limit as x goes to infinity of x over x squared. So I interpret that like this. As x gets very, very large, 1 divided by x is going to get close to 0.
Okay, so it's 0.
So this limit would be 0. And if this were upside down, for example, if I had the limit as x goes to negative infinity of x squared over x plus 1, then that reduces to x over 1, and as x goes to negative infinity, x over 1 will go to negative infinity. And what that tells me is that my graph does not have a horizontal asymptote. Instead, it drops down like that and goes out towards negative infinity as x goes out.
Okay, so going to x is on the top, then it is for the x on the, I mean,
Right.
yeah.
Right. You're comparing numerator to denominator, right? And the numerator is not growing at all. growing slower than the denominators.
Right.
If you find that the end model say something like x to the squared, would it then just be to either side would be going to positive infinity?
That's exactly right. And you think all the way back to when you did like polynomials and you looked at just the end model right there. And the even polynomials went to the same side on both sides. Okay. So what did we use limits for? Our biggest use for limits was to determine if a function was continuous. So f of x is continuous at x equals c if what? Somebody besides T. Ray and Josh. And Earl, who have all been doing gallantly. What does it mean for f of x to be continuous at x equals c? Emily.
Well, C. The left and right.
All that does is give you a value for this limit. If the left and right limits are equal, that means that this limit right here exists and has a value, but it doesn't give you continuity. It's not enough of that. I need something else. What has to be true about that limit if f is to be continuous at x equals c?
There's no discount.
Yeah? Yeah? That's it. It has to equal f of c. This is the behavior of f around c. This is the behavior of f at c. And if f is to be continuous at c, then the behavior around has to match the behavior at. That's what continuity is all about. This is one of the big ideas that we've studied this year, so it's a little disturbing to me that you guys are not bang with that. So you want to remedy that situation as quickly as possible. Guess where you can find it?
Study guide.
Yeah, how about that? Okay. Now suppose f is not continuous at x equals c. Then we say that f has a point of discontinuity. And of what types are they? 3 types. What? Removable or point discontinuity. Yes. So if not, then f has a removable discontinuity at x equals c if, what is the characteristic of a removable discontinuity? Yes, sir.
The limit from the left equals the limit from the right, but they don't equal.
Yes. Let's put it a little more simply, meaning the same as what you said. The limit as x goes to c of f of x actually equals some number. But that number does not equal f of c. And there are 2 ways that could happen. That could either happen if my function simply has a hole right there, or the function could have a hole right there, and it could have a value for f of c that is different from the hole. And the limit L will be the y coordinate of that hole, and f of c will be this guy right here. All right? What is the characteristic of a jump discontinuity? You? You?
Limit of f(x) like x goes to negative c,
Okay.
c negative,
And C positive has like different value.
Yep. And we pronounce that the limit from the left does not equal the limit from the right. Can somebody give me an example of a function that has a jump discontinuity?
Yeah, over X.
Nope. Yeah.
A piecewise function.
Some kind of piecewise function. Yeah, give me one.
Like, f of x equals x plus 1 when negative 1, oh, well, when x doesn't equal 0,
Okay.
and then x equals 4 when x equals 0.
Okay, let's check that to see if it has a jump discontinuity or not.
I think it
That's a,
Yeah. The limit as x goes to 0 from the left would be 1. The limit as x goes to 0 from the right would be 1. The limit exists. That's a removable discontinuity right there. So this is actually not correct. How can I modify this so that it would have a jump?
Okay. Check, okay.
Yeah.
X plus 1 when x is less than,
Okay.
and then 4x plus 4 when x is greater than 2.
That totally works. And does it matter that f of 2 doesn't exist? Nope, not a bit. We have a legitimate jump discontinuity. Why? Because it meets the condition right here. The limit from the left is 3, the limit from the right is 12. That's it. And then third is infinite discontinuity. Add x equals c. If what needs to be true about my function to have an infinite discontinuity? You're up. That's it. The limit goes to infinity. The limit as x goes to c, and f of x is equal to infinity, either plus or minus, and it could be one sign of infinity from the right and a different sign from the left, and that would still be an infinite discontinuity. As you can see, you will need to know these definitions and be able to use them lickety split. So don't try to resist that, simply go with it. Learn them. Right? Why do we care about continuity? We care about continuity because continuous functions have two lovely properties. They have extreme values, and they have intermediate values. And our picture is that we have some sort of continuous function on the interval a to b, and lo and behold, f has extreme values. It has a maximum and it has a minimum on the interval a to b. And it also has intermediate values. If I draw any horizontal line that is between f of a and f of b, then my curve has to cut through it if it is continuous. And so we express that like this. If f of x is continuous, on the closed bounded interval a to b, then first, extreme values. F has an absolute max and an absolute min on a to b. And second, if L is between f of a and f of b, then there is a C in a to b such that f of c is equal to L. And that's our intermediate value theorem, just like that. So we care about continuity quite a lot because continuous functions have nifty properties that we like. Another way of putting the intermediate value theorem is no teleporting. A function has to get from f of a to f of b has to go through all points in between. Yes, ma'am.
What do you use the intermediate?
That's a really good question. The intermediate value theorem, we're going to use it later on in order to establish that a function has to hit its average value somewhere. So this is the first reason that we care about continuous functions. Or sorry, this is the first use that we have of limits, that is to establish that a function is continuous, and if it is not, to figure out what kind of discontinuity it has. We used that in order to sketch functions, sketch rational functions. We used limits in order to find the places where f has vertical asymptotes. We used limits to find the places where f has horizontal asymptotes. We found the zeros, and we were able to sketch just from that information. If we have time, we'll practice that. I keep on wondering when the bell will ring.
It's like 40 minutes or so is this class.
Okay.
Is that longer?
All classes today are between 35 and 40 minutes. I've been keeping track. Only about 35. But
Because chapel went really long today.
Yeah. The second and major use of limits that we had is that limits gave us derivatives or instantaneous rates of change.
wow, 35.
And that brings us right to tomorrow.